little more with this because there is a section on squeeze theorem later. But I just want to introduce it a little bit because it applies to how we know these limits here. So there is a theorem called the squeeze theorem that can be used to find the limits of functions. And basically what happens here is that maybe we know a function g, this top one, and we know a function h, this bottom one. So we know those look like parabolas, I think, that have been graphed here. And then you have some sort of unknown function in between. You've got this function that you don't really know about. But you can prove that g is always greater than this function and h is always less than this function. Okay? So if this is true, and we know that the limit as x approaches c of h, bottom function, equals the limit as x approaches c of g, the top function. If g and h have the same limit, what do we have to know about f? It's got to have that same limit too, right? It's got to go to that same point, because if it's always between those two functions and those two functions meet, it's sort of squeezed in there, right, where we know that this function is there. So I'm going to show you just an example right here. So let's say that we've got some unknown function f of x, right? And so we got this unknown function f of x, and we know that when c equals 2, so when we're looking at the limit as x approaches 2, so let's see, right, we can think we're putting a 2 right there, right? We are looking at, we know that negative x squared minus 2 squared plus x minus 2 squared plus 3, which is going to be this blue graph right here. We know it's less than or equal to f of x, which is, f of x is some unknown function. We don't know what it is. And then we know that's less than or equal to that same function, but with a positive, so that's our red graph here. So if we know f of x is always between these two functions, we don't really know what it looks like, but we know it's got to go right there, right? So if we want to know the limit of this mystery f of x function, then we can just do the limit as x approaches 2 of either one of those other functions, right? So in this case, I'm going to do the x minus 2 squared plus 3. So I'm using this piece right here. You could use the bottom one if you wanted. And then this is a very simple limit. What do we need to do for it? Yep, just put the 2 in. So 2 minus 2 squared plus 3. It's just going to give us 0 plus 3, so we get 3 will be our limit for that. Okay. So here is an example of a type of question that you might see. So they give you the function f is defined for all x in the interval from 2 to 7. Which of the following statements is true, if true, implies that limit as x approaches 4 of f of x equals negative 5? So I don't know what f is, but I need something that's going to give me information that the limit as x approaches f is going to equal negative 5. So A talks about there being a function g where we know f is always below g, and we know the limit of g. Okay, so I've got, let's do, here's f, and I know f is always less than or equal to g. So that could look like this, right? G could be way up here. Is there any guarantee they're going to have the same limits there? Because we're only talking about one function, right? That can't be, you can't have a squeeze theorem with just one other function that you know about. So it's not going to be A. B has a similar problem. You're only talking about this one other function, G. So it's not going to be B. Because basically the only thing that was switched for that is G of X is less than F of X. So now G is below F. still. There's only like one other function. It doesn't tell us anything. So here we've got there exist functions g and h. So now we're talking about two functions. And this tells us that f, which is our unknown function, that's the one we want to know about, right, is less than g, so g's up here, and that's less than h, so h is up here. Does that help us know what f is going to be? It would help us know what g is going to be if we knew what f was, but f is not being squeezed there. It's not the middle function, right? So c is not it. D is going to be our answer because here f is in between, right? So we know f is always between g and h. So we've got g is on top, h is on bottom, f is between those. So if we know g and h have the same limit, then f would also have to have that same limit. So D would be our answer for that one. Okay, so let's look at, I don't even think I'm going to do 3 right now for the sake of time. I want to look at why I even put that here, okay? So let's talk about, just real quick, I'm going to give you some squeeze theorem on this, and then you're going to look at these special trig limits, and you're going to like memorize them and take my word for it and not worry about it too much again. But let me show you why squeeze theorem is even here. So I'm looking at the limit as x approaches 0 of sine x over x. And I'm saying that it is 1. But if I plug in 0, right, sine of 0 over 0 is 0 over 0, which is indeterminate form. And we did not learn anything yesterday where we can't factor that, we can't rationalize it, we can't do complex fraction sort of stuff. We don't have any skills for dealing with that yet, right? So, as far as figuring that out, it's very difficult. But let's think about what we've got here. Just real quick, squeeze theorem explanation. So, sine of x, it has a maximum value and a minimum value, right? When we think about that sine graph, right, it goes up and down. It does not go above a certain point or below a certain point. What's the very highest I can have on a sine graph if it's just a plain sine graph? 1. The very biggest you can get for sine is 1. So sine of x is always less than or equal to 1, right? What's the lowest I could have? -1. So sine of x is always between -1 and 1. All right? Now, I'm not talking about sine of x. I'm talking about sine of x over x. So, because if I'm just doing the limit of sine of x, that's no problem. That's direct substitution. I just plug it in, right? Because sine of 0 is 0. 0 is fine. That's a good answer to get. I just can't get 0 over 0. So I'm talking about sine x over x. So I'm going to put this over x. And if I divide that by x, I have to divide these by x. Right? Okay. Now, I do not know what this limit right here is. Right? But let's go over here and let's pull up Desmos because it's most helpful here. And let's graph this. Okay, I'm going to graph y equals -1 over x. I'm going to graph y equals +1 over x. Now I'm doing this wrong. What have I got to do? Because those are in, gosh, there's something different. It does it here, doesn't it? What am I doing now? I might have to go back. I've forgotten. Why am I doing this wrong? It's something about this, but I've done it wrong. I know that has squeeze theorem, but I've forgotten what I was supposed to know about that, apparently. Don't even worry about it right now, okay? We can do these without this. Okay, I'm going to go back and look at that. Let me make myself a note over here. Squeeze theorem. Whew. I'm going to go back and look at it. But we've not got time right now for me to figure it out. I could do it, but it'll take me a minute. So this comes from squeeze theorem. And I've forgotten why. Because there's something else I've got to do that I can't remember because when I graph it, it's wrong. Okay. Forget that last 3 minutes there. And take my word for it, because it says so in the book right now, that the limit as x approaches 0 of sine x over x is 1. I promise it's true. And I could prove it to you, but I've forgotten how to prove it to you, apparently. It is also true that the limit as x approaches 0 of 1 minus cosine x over x is 0. Okay? These two you need to have memorized. Okay? They have to be memorized. You need to know them because we have to have them to be able to do these problems. Right? So the problems that we're going to get, we're going to try to deal with this in being able to do these problems with trig. Okay? Now, if we look at example 4, if I try to plug in 0, I would have sine of 0 over 7 times 0. And what was sine of 0? Is 0. 7 times 0 is 0. That does not equal. We can't use direct substitution on this. Just like the other problems, you want to try direct substitution every time. It doesn't work here. So, here is what we are going to do. When I have the limit as x approaches 0 of sine x over 7x, can I write it like this? Is this equivalent to the original problem? Yeah. It is, right? Because if I multiplied it back together, I'd get sine x over 7x, right? So, our properties of limits told us that if we had a coefficient, because 1/7 is just a coefficient, right? It's just a number. I mean, it's a fraction number, but it's still just a number. That if I was multiplying a function by a coefficient, I could just, like, multiply it by the answer, right? I could just, like, pull that out front. So, I can do that, which means I've got 1/7 times the limit as x approaches 0 of sine x over x. Now, what did I tell you up here the limit as x approaches 0 of sine x over x is? 1, right? So I can replace that whole thing with 1. 1/7 times 1 is going to give us 1/7. Okay, questions on that? All right, let's look at example 5. Do our special trig limits having tangents up here? They do not. So what can I do with my tangent? I can't just change it to cosine. Sine over cosine, right? Tangent equals sine over cosine. So I can do the limit as x approaches 0 of sine x over cosine x over x. And that's a complex fraction, and I don't like complex fractions, so I'm going to put this over 1. Dividing fractions is easy as pie. I'm going to flip the second and multiply. So sine x over cosine x times 1 over x is going to give me this, the limit as x approaches 0 of sine x over cosine x times x. Now, that's still not a special limit, right? But let's think kind of like we were thinking on the last problem where I had that 7 that was kind of in my way. So like right here. Yeah, so what we can do on this is we can write it this way. Limit as x approaches 0. I can do sine x over x, and then I can do times 1 over cosine x. And just let's. So what I'm looking for is like I see, oh, I've got a sine x over x right there, but I have that extra cosine, so I'm just kind of like split these apart. I can do that because it's all multiplication there. Okay, so now here this is a little bit different than the last problem because this was just a coefficient, so we could pull it out. This has an x. We cannot just pull it out. But our properties of limits told us if I have limit of something times limit of, or times something else, I could just do limit of the first times limit of the second, right? So I'm gonna write this. This is like overkill, but I'm gonna do it just to be very clear what's happening here. Limit as x approaches 0 of sine x over x times limit as x approaches 0 of 1 over cosine x. So this stuff right here is the special limit. What does it equal? 1. And then I would be doing the limit as x approaches 0 of 1 over cosine x. So I would be plugging in 0 for that x right there, which makes me feel like I'm going to get 1 over 0. But what's cosine of 0? It's right here. That is 1, 0, x coordinates cosine. So I get 1 times 1 over 1, which is just 1. Okay, questions? All right, 6 looks a lot like 4, but it's going to be different. Or it's good. Mathematically, it's very different. There's a way you could kind of understand this that you're going to get the right answer every time, but it's really bad understanding. So it is going to be just 4. But the reason it is just 4 is different than the reason that the other one was just 4. Now, you can kind of get away with just saying it's 4. You can kind of get away with that. But let me show you. You got to think about it a little bit differently. So the difference here is whenever the 4 is in the bottom, I could just kind of separate it out. But I cannot just like pull a 4 out of my sign. That is not mathematically correct to do that. And in fact, when we're talking about the test, whenever, like if I did that, I'm going to write this down, don't write it down. If I did this, if I did 4 times sine x over x, and then I said the limit, or well, I don't even need limit anymore, and then I just said that is 4 times 1, which is 4. 4 is the correct answer for this. But if this were on free response, you would lose a point for this because it's what they consider a linkage error. So like if, for a real simple linkage error, so if I was doing 2 times 3 minus 7, and I did 6 plus 7, and then I did negative 1. Did I get the right answer? Is my work right? No, because I accidentally wrote a plus right there instead. That's a real basic example of a linkage error. If you write down something that's false and you say it is equal to what was before, then you lose a point on that if they catch it. I don't always catch those necessarily. Sometimes I'm grading too quickly, but and I don't know how. I've never been a grader, so I can't say how often they catch the linkage errors. But if they catch something that's false in between, you do not get credit. So if you were to write this, you would not get. If it's worth 2 points, you might get 1 point for the answer, but like you would have a linkage error there because this is not correct. Oops. Let's see. I just wanted to mark that out. This is not correct to say because we can't take a 4 and pull it out of the sign. So let me tell you how you got to deal with this. So if I have a sine of x over x, and I'm doing that limit, I know I get 1, right? Now, it does not have to be an x. It could be anything. So that x right there doesn't have to be an x. It could be the sine of, it could be the sine of Troy over Troy as Troy approaches 0, that equals 1, right? It can be anything. It doesn't have to be sine of x over x. It could be as long as what is here, as long as what is here, here, and here all match. Actually, I don't even think I have to change that x right there. Either way. As long as the stuff matches, it still equals that value. So, what I can do here is I can put a 4 right here if I also put a 4 in the top. Right? Because if I put a 4 in the top and the bottom, 4 divided by 4 is 1. I haven't changed the value right here. So now this 4x and the 4x match on top and bottom. So what I could write here is I could do limit as x approaches 0 of 4 times sine of 4x over 4x. This stuff right here, whenever we take that limit, we're going to get 1. So we would get 4 times 1, which equals 4. So whenever your number is on the inside of your sign, the way you think about it is different than whenever it's on the bottom. It does end up working out where it looks like you just pulled the 4 out and that was your answer. It's going to happen with pretty much all the problems. So, as long as it's not shown up on free response, which it probably won't, we don't have to worry about it too much. Okay, let's look at this one. Secant x minus 1 over x. Our special limits had nothing to do with secant, right? So what do you think we're going to probably have to do with that secant? Turn into something else. What is secant? No, cosine over sine is cotangent. Okay. We're also going to have a quiz on trig identities. So let's jot these down over here. So tangent, I'll give you the full thing. Tangent is sine over cosine. We used that one just now. Okay. Secant is 1 over cosine theta. Cosecant is 1 over sine of theta. I always remind myself you have to have a co in every pair. So secant can't go with sine because there wouldn't be a co. Right? And cosecant can't go with cosine because there would be 2 cos, and you can't have that either. So secant has to go with cosine. Cosecant has to go with sine. There's something else they told me at training about how to remember that. And I can't remember what it was. I'm going to look through my notebook and see if I can find it. My brain's getting old. Alright, so secant is 1 over cosine. So limit as x approaches 0 of 1 over cosine x minus 1 over x. Now, when we have complex fractions, there's a couple ways we can use to deal with those complex fractions. One thing we can do is get a like denominator in the numerator part, and then we can flip and multiply. There's another way that I really like to use whenever you only have one single denominator, And that is, I could do this. I could multiply this whole numerator by cosine x. And then I could multiply the denominator right here by cosine x. The reason that I'm doing that is because when I'm doing this over here, I'm doing cosine x times 1 over cosine x minus 1. Right, I'm distributing here. And here I'm doing overkill work here. So that's going to be cosine x times 1 over cosine x minus cosine x. What happens right here with this cosine? That cosine x, it's over 1, right? What happens with that cosine right there? They cancel, and we're just going to get 1 minus cosine x in that numerator. 1 minus cosine x. And then in the denominator, I've got x times cosine x. So if I look back at those special limits, you can see we had this other one. It was 1 minus cosine x over x, and that equals 0. So 1 minus cosine x over x, this piece right here, right, whenever I do that limit, I'm going to get 0. So I'm going to write it out as specifically as I can, but if you skip this step, it's okay. So that's going to be limit of 1 minus cosine x over x times limit of x approaches 0 of 1 over cosine x. So all of this stuff was the special limit that we're going to memorize, and they told us it was 0. This did a poor job of proving us anything about that, but we're taking their word for it right now. Then over here I'd plug in my 0, 1 over cosine of 0. What is cosine of 0? 1. It really doesn't matter that much what it is as long as it's not 0, because 0 times anything is 0, so you get 0. You will find on these trig problems, if you have no idea what to do, it is a good idea to guess 1 or 0 as your answer, because you're going to get a lot of 1s and a lot of 0s. It's not always. We did have the 1/7 and the 4, but we did see those other numbers in there, right? So it's a good idea to guess 1 or 0. All right, what do you guys think on this one? We're probably not going to get to the last few examples. We're probably just going to do the trig today. One minus cosine squared. It is a thing. It is sine squared, right? Because we know sine squared plus cosine squared, theta there, equals 1. So like if we subtract that cosine squared, we know that sine squared theta equals 1 minus cosine squared theta. So limit as x approaches 0 of sine squared x over x. All right, now that kind of looks like sine x over x, but it's not sine x over x because our sine is squared. Kind of. What do you mean by taking it out? Yes. We could do sine x times sine x over x. Now, this piece right here equals 1. And then we got the extra sign over there, but it's in the numerator. It's not going to give us a 0 in the denominator. So we would have limit as x approaches 0 of sine x over x times limit as x approaches 0 of sine x. And so this is 1. What do we get when we plug in 0 here? We would have sine of 0. What is sine of 0? 0. So we get 0 for for this answer. I'm telling you, if you need to guess, 1 or 0. 0 might even be more common because if you got to multiply by 0, you're going to get a 0 no matter what the other numbers are. So, let's see. I, a lot of times, skip this one because I've about decided we don't need to know how to do it. And I think I'm going to skip it. Let's see. I don't think I have time to do the E's and the, well, it's just E's, but I don't think I have time to do the E's and do it justice right now. So let's just stop with it and we'll do the trig. So that means on your assignments, let me see, you guys are going to do, yeah, I think we're okay. So we're going to do 69 through 78 tonight. Okay, so 69 through 78. Don't do 97 through 102 or 79 and 78. Let me see if there's anything I need to remind you about. I don't think so. Keep in mind, you need to check, I'm not doing this, I've been not doing a good job. You need to check direct substitution on all these too. Because on this homework, there's one everybody always comes in asking me about. And they're like, I don't even know what to do with this, Miss Hyatt. And it's just a direct substitution problem. You just plug the number in. So there is one of those that's direct substitution. I think that's the one I usually have the most. Maybe 2 of them that are direct substitution. So. We'll pick up the E.